So what we're going to move on to in this final lecture looking at complex numbers in computer science is something that's maybe a little bit unusual. It's how complex number properties have been used in artificial intelligence applications as a means of assisting with computer creativity. So the main areas have been in creating abstract images and in what I'll describe at the end, computer musical composition. So the object that plays a major role in this work are complex number sequences. So what we have is the behavior of certain types of complex number sequence has led to these being exploited in specialist area of artificial intelligence called computer creativity. So the two main areas: building intricate graphical images, composing musical scores. And what I'm going to do in this lecture is have a look at the main ideas that support these techniques from complex numbers. So, the most important notion is an object that's called an iterated function sequence. And what all these do is they tell us how to construct a sequence of complex numbers when we start from some initial value. So let's look in more detail at that. What's an iterated function sequence? Well, we start off with some complex valued function. So if we have some function that maps some complex numbers to complex numbers. And what we refer to as the nth iterate of that function, we use this notation to describe that, is that's the outcome when we apply that function n times to a given starting value. So what do I mean by that? This function, if we haven't started yet, if n equals 0, that's just the value of the input parameter. If we've already started, then it's the value of the function applied to the last value that was generated. So, why are these of interest? Well, what we find is they very often have particular behavior. They allow us to split the complex plane into two separate parts, and these parts are relative to some parameter which is called the escape radius of the function. So we have a set of complex numbers, those that are inside, and these are the set of complex numbers for which no matter how often we iterate the function, the size of the complex number that results is always bounded. The other region, the set of complex numbers which are outside, these are the set of numbers in the complex plane for which at some point we iterate the function enough times, and that's going to give us a complex number whose value is larger than the radius we are looking at. The other object that these give rise to is a notion called an orbit. So what we have is a sequence of complex numbers from this one, up to the largest member of the sequence, and these have the property that when we apply the function to the first element, we get this one. If we apply the function to the middle element, we get this one. But when we apply the function to the last element in the sequence, that takes us right back to the start. So iterating the function starting from this point here, that just takes us round in a circle, in an orbit, as it's referred to. The escape radius we need to use, the size parameter here, very often it suffices just to set that as low as a value 2. The class of functions which turn out to have particularly interesting behavior with respect to iterating them many times are complex quadratic value functions. So in particular, those which take the input value, they square it, and they add some constant complex number onto the end. So there's a structure which has been very widely studied called the Mandelbrot set. And what this does is this classifies how this function behaves for those constants for which when we start this quadratic function, iterating it with an input value 0, then the constant that we chose always results in a complex number whose size is at most 2. So we have a set of complex numbers for which when we iterate this function starting from 0, then we never get a complex number larger than 2. When we start this function iterating from 0 for other complex numbers, then at some point the size of the complex number that results is bigger than 2. If we fix C, fix this constant, again using a radius 2, then the set of complex numbers that we can set as a parameter, which result in the function never exceeding the value 2, the set inside, this is called a Julia set. And the other numbers, the complex numbers which take us outside, this is referred to as a Fatou set. So here's the outcome of plotting the Mandelbrot set in the complex plane. And we can see some interesting features in this. If we look at this region here, that's exactly the same structure as this region. It's exactly the same structure as this and this. So what these objects are demonstrating is a property called self-similarity. The way in which these behave is by composing exactly the same basic structure many, many times, doing this infinitely often. So that's a Mandelbrot set. Now, there's an obvious problem with computing and displaying Julia sets. It's quite clear that since this object is defined with respect to behavior as we iterate infinitely often, we can't actually validate whether a given point is inside the Julia set or outside. We would have to iterate the function infinitely often. In practice, however, it turns out that if we iterate a sufficient fixed number of times, for example, if we set n to be 1,000 or n to be 10,000, that gives us a good enough approximation to the outcome. And when we're displaying the result of computing a Julia set, a method that's very often used is to use some kind of color mapping convention to highlight the structure itself. And one way we can define the colors that are used is to set the color that's used for the complex number based on the number of times we have to iterate the function in order to go outside the escape radius. Now, the notion of Julia set is not limited just to complex quadratic functions. It can in fact be shown that this is a well-defined notion for any complex rational function. So functions in which we're dividing one complex valued function by another complex valued function where both of the functions involved are complex polynomials. So here's an example. Here we have the complex function. We square the input number, and we add this complex constant value into. And when we plot that, the outcome is this form here. So we have the same self-similarity structure that we had with the Mandelbrot set. This object is identical to that object. This object identical to that object. This to this, to this, and to this. So this is quite an intricate form we already have, even though it's just a quadratic function that's being used. If we take another example, here we have the Julia set corresponding to a complex cubic function. We take our input value, we cube it, and we add a particular complex constant value on. And we get this. If we plot the structure in the complex plane, this is a result. And again, we have this notion of self-similarity. We have three parts to this structure, this one, and this one, and those individual parts are made up in very much the same way. This, and this, and this. I'm going to finish off a discussion of complex numbers by looking at some fairly recent work in how complex numbers and this notion of Julia set have been exploited as a means of composing music. So in 2001, an American academic, a lady called Elaine Walker, in her master's dissertation, which was produced at New York University, she explored how this notion of orbits in a Julia set could be used as a compositional technique. So if we take a typical Julia set, especially a quadratic function Julia set, we find this contains very many different orbits which have different lengths. So sometimes we have very simple orbits of length 2 or length 4. Sometimes we can find quite complicated orbits involving several tens or even several hundreds of elements. But what this notion of orbit provides is it gives a kind of unifying collection of basic building blocks which we can use to experiment and to build compositional structures on. So we look at the elements in an orbit. Well, these are just complex numbers. So what we can do is we can take the two parts of a complex number, the real part and the imaginary part. Now both of those are real numbers, so we can map from a real number to some sort of standard sound convention, something such as MIDI, something such as notes on a standard musical score. And by doing that, we get quite intricate musical scores can be produced as a result. One thing that Ms. Walker did in her work, she discussed instrumental design for creating scores from orbits and Julia sets, so-called chaos melody techniques, and these are produced by looking at different starting points. Now, the assertion that the outcome from this kind of composition sounds pleasing, this goes back to a claim that what Julia sets are exhibiting concerns something called their fractal dimension. So in classical dimension, we use whole numbers. A square has dimension 2, a cube has dimension 3, a line has dimension 1. In what's called a fractal set, we have objects which have dimension which belong to the rational numbers. So we can talk about objects with dimension 1/2, dimension 1/3, and so on. Two American physicists in the 1970s, they conjectured that the reason why particular structures appeal to the senses is because they have a certain fractal dimension close to 1. So Vos and Clark, they carried out experiments to test this hypothesis. In order to do this, one of the things Vos developed was a random, what is called 1 over f music algorithm, which uses a dice throwing technique. And what this does is this allows us to map numerical outputs onto traditional scores. So here's one example of that. This is a traditional score that is produced using a Vos algorithm. If that doesn't make a lot of sense to you, so here's a very basic example of output from Vos piece, just a short 1-minute section. So let me just summarize by seeing what we've seen with the use of complex numbers in AI. This is still a very active field, by the way. So the exploration of ideas that use complex number function, iterating complex number functions, this is provided a very rich source of work in a specialist area of artificial intelligence concerned with computer aesthetics, computer creativity. And a lot of those take as their starting point this notion of a fractal set. So in addition to these kind of abstract image structures from Julia sets and variations on these, where we find applications are in, for example, computer graphics imagery in building artificial landscapes. So these might occur in PC games. They've been used to develop artificial landscapes in science fiction and fantasy films. In musical composition, there have been a number of modern composers that have developed PCs based on complex number computation. So people such as Karl-Heinz Stockhausen, people such as Pierre Boulez. There are groups such as the French Research Center, IRCAM, which have developed techniques based on this. Okay, so that finishes our review of complex number theory. What I'm going to be moving on to in the next section of this lecture are looking at computation as experiment.